In this video, we'll introduce the cross product of two vectors in R3, which results in a vector that's orthogonal to both input vectors. Then we'll also discuss least squares approximation in the context of continuous function spaces. So one thing to be aware of is that the cross product only exists in R3 and not in other dimensions. So first, we're going to change the notation slightly, right? So for the standard basis vectors in R3, we're going to call them I, j, and k, right? So where the vector I is just the vector 1, 0, 0, the vector j is just the vector 0, 1, 0, and the vector k is the vector 0, 0, 1. So that if you take any vector in R3 with coordinates say v1, v2, and v3, written in terms of the standard basis vectors, it'll just look like v1 times I plus v2 times j plus v3 times k. Okay, so with that in mind, the formula for the cross product is written here, right? So u cross v, again in terms of the standard basis vectors I, j, and k, you calculate the individual components like so. However, another way to calculate this determinant is to set it up as a 3x3 determinant. Right, so the 3x3 determinant is set up like this, where on the top row you just write out the standard basis vectors I, j, and k. The second row are the three components of the vector u, and then the third row are the three components of the vector v. And so if you expand out this 3x3 determinant by cofactors along the first row, it'll look exactly like this, right? So if you remember, there should be an alternating sum, right, from the terms, right, plus, minus, plus. And then if you write out the 2x2 determinants for each of these submatrices, you get this, and if you look back at the formula here, you can see that they're exactly the same, right? So so I'll be calculating the cross product by using this 3x3 determinant and then expanding it out like this. Okay, so let's look at an example of calculating the cross product. Okay, so here I have the vector u is I minus j minus k, and the vector v is I plus 5j minus 3k. This should be the vector k. So written in terms of the coordinates, right? So it's just the coefficients of I, j, and k. So the vector u is just the vector 1, negative 1, negative 1, and the vector v, right? So again, it's just the coefficient. So it's 1, 5, negative 3. Okay, so let's calculate the cross product, right? So u cross v, we set up the 3x3 determinant. So I, j, k on the top row. And the second row are the components of u, so 1, minus 1, minus 1. And the third row, components of v, 1, 5, and negative 3. Okay, so now we expand by cofactors, right? So first for I, so it should be these four entries. So negative 1, 5, negative 3, and minus for j. Okay, so it should be these four entries. So 1, negative 1, 1, negative 3. And then for k, so it should be these four entries. So 1, negative 1, 1, 5. Okay, so now we just do the 2 by 2 determinants. Right, so this is so this times this minus this times AD minus BC. Right, so this is positive 3 minus a negative 5, which is 8. And then this term is negative 3 minus a negative 1, which is negative 3 plus 1, which is negative 2. And then the last one, so 5 minus a negative 1, which is 5 plus 1, which is 6. Okay, so then it's just 8i, then minus minus becomes a plus, so plus 2j plus 6k. And then written just as coordinates, this is just 8 comma 2 comma 6. Okay, so this is what we get for u cross v. Okay, so now let's calculate v cross u. Okay, so again, we set up the 3 by 3 determinant. So I, j, k on the top row. Now v goes in the second row, right? So v is 1, 5, negative 3. Then u goes in the bottom row, 1, negative 1, negative 1. And now we expand. So for I, it's these 4 entries. So 5, negative 3, negative 1, negative 1, and minus. J is these 4 entries. So 1, negative 3, 1, negative 1, and then K is these 4 entries. So 1, 5, 1, negative 1. Okay, so now let's calculate. Negative 5 minus 3 is negative 8. Negative 1 minus the negative 3 is negative 1 plus 3 is positive 2, but then minus here, so that's minus 2j. And then negative 1 minus 5 is negative 6. Or written in components, this is negative 8, comma negative 2, comma negative 6. Okay, so one thing you should note here is that u cross v is not the same thing as v cross u, right? So the cross product is not commutative. But you can see that v cross u is the negative of u cross v, right? So so what this means is that the cross product is not commutative, but it's what's called anti-commutative. On this page, we'll discuss some of the algebraic properties of the cross product. So most of these properties listed here essentially follows from thinking of the cross product as a determinant, right? So let me just write it again over here. There's a u cross v. You put I, j, and k on the top row, and then the components for u on the second row, and then the components for v on the third row. Okay, so the first property, right, so says that the cross product is not commutative, but it's what's called anti-commutative. Right, where u cross v is minus v cross u. So the reason that it's anti-commutative is because, so this property follows from the property of determinants, that if, so basically what happens is for v cross u, right, you're just switching the role of v and u in this determinant, right? So the v's would now be in the second row and the u's would be in the third row. And so the property of determinants when you swap two rows is that it changes the determinant by a minus sign, right? So if you go back to section 3.2, right? So if you interchange two rows, then determinant of B is minus determinant of A, right? So, these are the properties of determinants that we've discussed previously. Okay, so that's the anti-commutative property. And then property 3, right? So C times U cross V, right? So if you either multiply U by C or V by C, right, that's just multiplying either this row by C or this row by C. And again, from the property of determinants, if you multiply a single row, if you multiply a single row by a scalar, it's the same thing as multiplying the whole determinant by the scalar, right? And so that's exactly what property 3 is saying. So one other thing to be careful about is that the 0 that's written in properties 4 and 5, so the 0 is bold-faced, right? So that means that this is referring to the 0 vector and not the number 0. When we're working with cross product, everything is vectors, right? So the result of the cross product should be a vector and not a number. And so this 0 is the 0 vector and not the number 0. And again, it follows essentially from if for property 4, right? So if the last row is all zeros, then when you expand, do the cofactor expansion in the subdeterminants, the 2 by 2 determinants each have a row of all zeros, and then so that means that each of the components for I, j, and k becomes 0, so you get the 0 vector. And then similarly for property 5, if you have two identical rows in a determinant, then the determinant is 0, right? So again, when you expand, do cofactor expansion, the subdeterminants all have determinant 0. And then finally, in property 6, right, so where you're mixing the dot product and the cross product, right, so this calculation, first of all, makes sense, right, because the result of V cross U, the result of V cross W is a vector, and so you're taking the dot product of two vectors, right? So the result of this is a number and not a vector. So this is what's called the triple product. And the triple product, instead of calculating in two steps where you first do the cross product like this, take the result of that, and then calculate the dot product, you can actually calculate it all at once using a single determinant, right? So the way you set it up is so you have three vectors u, v, and w, right? So if they're written in this order, then the vector u is written in the determinant as the first row, the vector v is now in the second row, and the vector w is in the third row, right? So now, by setting up the determinant this way, every single entry of the determinant is a number, right? So the result of this determinant is a number or a scalar. So the reason that you can set it up in this way, right, is because, I mean, if you do the calculation in two steps, right, so first you would calculate the cross product by setting up this determinant, right? And so that would look exactly like this for V and W. And then if you then take the dot product of U1, U2, and U3, it would look like this. And then this thing is just the cofactor expansion of this thing, right? And so so to calculate again the triple product in a single calculation, you can just straight away set up this determinant. And then finally, to compare these two, again, it's just a matter of swapping the rows in the right way to see that the two things are equal to each other. Okay, so these are some of the algebraic properties of the cross product. Here we'll discuss some of the geometric properties of the cross product. So the first property we mentioned previously, right? So when you calculate the cross product of two vectors, the result of that is orthogonal to both the input vectors, u and v. So this can be visualized in 3 dimensions in this way, right? So say you have a vector, two vectors u and v. So the span of u and v forms a plane in 3-dimensional space, right? And the resulting cross product is perpendicular to both u and v. So the reason is if you calculate this out, right? So what does it mean for two vectors to be orthogonal? It means their dot product is 0, right? So if you calculate the dot product of u with, say, u cross v, then this is just a triple product, right? And where this vector and this vector are the same, right? So if you go back and set up the triple product like this, right? So this row and this row are going to be exactly the same. But for a determinant, if two rows are the same, then the determinant is 0. And then the same thing for v, right? So if you do v dot this, then you have two rows that are the same, so the determinant is 0. Okay, so that's where property 1 is coming from. So another thing is that so we see that the result of u cross v is orthogonal to both u and v, right? And if you want a unit vector from that, then you can just divide by its length to produce a unit vector that's orthogonal to both u and v. In terms of the other properties, property 4 essentially just follows from property 2, right? Because if you sketch in a parallelogram formed by u and v like this, then the area of the parallelogram is just the length of the base times the length of the height, right? But then the length of the base is just the length of u, and then the height is v sine theta, right? Because you have a right triangle here, and then the right triangle sine theta is opposite over the hypotenuse, right? So then this is just this times sine theta, and then so if you write it out like this, then from property 2 it's just the same as the norm of the cross product. Property 3 also follows from property 2, right? Because they're parallel if the angle is 0, right? So if sine theta is 0, then u and v are pointing in the same direction, right? So the angle is 0 when they're parallel, but then sine of 0 is 0, right? So then the length of the cross product is 0, but the only way for the length of the cross product to be 0 is the cross product itself to be the 0 vector. So property 3 also follows from property 2. Okay, so the second topic of this section is least squares approximation in the vector space of continuous functions. So the idea is the following, right? So you're given some continuous function, let's say f of x, we want to be able to approximate it with some simpler function g of x. So maybe a polynomial or something. So first let's recall that the vector space of continuous functions has as this inner product, right? So the inner product of two functions f and g is the integral over the interval of the product of those two functions. And so taking this inner product, right? So in this context, the least squares approximation means minimizing the squared distance between two functions, right? So again, the norm of a function is the square root of the inner product of a function with itself, right? So this is just how you calculate a norm in an inner product space, right? So and then the inner product of function itself with just the integral squared, right? So that means that we want to minimize the squared norm of the distance between the two functions, and so writing it out as an integral, it's this integral of f of x minus g of x squared. Okay, so there's a couple of things to be aware of in this kind of least squares approximation for functions, right? So first, in Calc 2, you already have a method of approximating functions using Taylor polynomials. So this kind of least squares approximation is a different kind of approximation from Taylor polynomials. And then the second thing to be aware of is that because a continuous function on an interval has a continuous set of points and not a finite discrete set of points, we can't use the methods of section 5.4, right? So because to be able to set up the matrix equation AX equals B, the input for A and B is a finite set of points. But again, a function f of x has a continuous set of points on this interval. Okay, so the definition here is just, again, saying that a least squares approximation means trying to minimize the squared norm in this way. Okay, so let's go over how we'll calculate least squares approximation for the continuous function space. Right, so it's going to be based on this theorem here. So essentially, what happens is that the approximating function g of x will belong to some finite dimensional subspace of the vector space of continuous functions, right? So remember that this vector space is infinite dimensional. So we want to take a finite dimensional subspace and then for the finite dimensional subspace have an orthonormal basis, and once we have the orthonormal basis, we just write the approximating function in terms of the orthonormal basis in this way. Okay, so in this example, we're going to try to find the least squares approximation of the square root of x over the interval from 0 to 1 using a second degree polynomial. g of x. Right, so again, to be able to apply this theorem, so this method, we need a finite dimensional subspace for g. Right, so here, because g is a second degree polynomial, our finite dimensional subspace will be P2. And so if you remember, P2 has as a standard basis the vectors 1, x, and x squared. However, the standard basis for P2 is not orthonormal with respect to the inner product for function spaces, right? So because we're dealing with the continuous function from A to B, and P2 as a subspace of this vector space, we need to use the inner product from the continuous function space, which is exactly this inner product. Right? And so the standard basis is not orthonormal with respect to this inner product. And so to obtain an orthonormal basis, we can apply the Gram-Schmidt process to this basis. And so the calculation for that is not here, but essentially you get this orthonormal basis after applying the Gram-Schmidt process to the standard basis. Right, so these three vectors will be our vectors W1, W2, and W3 in calculating this expansion. Okay, so now to find the approximating function g, I just need to calculate the coefficients for these three vectors in this expansion, and the coefficients are just calculated as the inner products of f against the three orthonormal vectors. So let's do that calculation, right? So first we need to do f with W1. Okay, so what is the inner product of f with W1, right? So we need to integrate the intervals from 0 to 1. F is the square root of x times, and W1 is just the function 1. And the square root of x is, we can use the power rule to integrate, right? So square root of x is just x to the 1/2 power. And then the power rule for integration says you add 1 to the exponent and you divide by the new exponent, right? So the antiderivative of x to the 1/2 would be x to the 3/2, right? Because 1/2 plus 1 is 3/2. And then divide by 3/2. But dividing by 3/2 is the same thing as multiplying by 2/3. Right, so this is 2/3 x to the 3/2. And then evaluating it at the endpoints, if you plug in 1, you just get 2/3. If you plug in 0, you get 0. Right, so 2/3 minus 0 is just 2/3. Okay, so the first coefficient is going to be 2/3. Okay, so now we have to take the inner product of f against W2. So again, the integral from 0 to 1, f is the square root of x, then times W2 is this function here, so square root of 12 times x minus 1/2 dx. Okay, square root of 12 is just a constant, so I can pull that out of the integral. Integral from 0 to 1, and then square root of x is multiplying this thing in parentheses, I distribute, right? So square root of x times x, this is x to the 1/2, this is x to the first. So multiplying them, you add the exponents to the x to the 3/2. Then you have minus 1/2 square root of x, so minus 1/2 x to the 1/2. And then now the antiderivative. So the square root of 12 is outside. The antiderivative of x to the 3 halves is x to the 5 halves divided by 5 halves, but dividing by 5 halves, same thing as multiplying by 2/5. Right, so you get 2/5 x to the 5 halves, then minus 1/2, and then again adding 1, you get 3 halves, divided by 3 halves is the same thing as multiplying by 2/3. So it's 2/3 x to the 3 halves. Evaluated from 0 to 1. So square root of 12 is outside. If you plug in 1, here you get 2/5. Then plug in 1 here, this is just 1, so 1/2 times 2/3 is 1/3. And then if you plug in 0, this is 0 and this is 0, so the whole thing is 0. Okay, so the result is this, and what is 2/5 minus 1/3. So as a fraction, 2/5 minus is 1/15. So this is square root of 12 over 15. Okay, so that's the second coefficient. And then finally I have to calculate the inner product of f with W3. Okay, so integral from 0 to 1. What was f? F was the square root of x. And times W3, which is this vector, so square root of 180 times x squared minus x plus 1/6. Okay, so again, this is a constant, so it comes out. And then this x to the 1/2, I have to distribute it. Right, so 1/2 plus 2 is 5 halves. 1/2 plus 1 is 3 halves. And then this is just times a constant, so you got plus 1/6 x to the 1/2. Okay, so now we take the antiderivative. So 5 halves plus 1 is 7 halves. And then dividing by 7 halves is the same thing as multiplying by 2/7. So you got 2/7 x to the 7 halves. This is 5 halves and 2/5, so 2/5 x to the 5 halves. And 3 halves and 2/3, so plus 1/6 times 2/3 x to the 3 halves. Evaluated from 0 to 1. Okay, so you get square root of 180. Plugging in 1, this is 1, this is 1, this is 1. So you just get left with the coefficients, and then plugging in 0, they're all 0. So what is this? This is 2/7 minus 2/5, and then 2 cancels a 2 here, so you get 3 times 3, so that's 1/9. Okay, so you get, so what is this? So 2/7 minus 2/5 plus 1/9. What is this in fraction form? So it's 1 over 315 minus 1 over 315. So this is minus square root of 180 over 315. Okay, so we have our 3 coefficients. Right, so what does that mean? Right, so these are the 3 coefficients in expanding G with respect to the orthonormal basis. Right, so this means that g of x is 2/3 times w1 plus square root of 12 over 15 times w2 minus square root of 180 over 315 times w3. Okay, so this is in terms of the orthonormal basis, but if I wanted to know what g is in terms of x squared and x and 1, I need to plug in the orthonormal vectors into this and expand it out. Okay, so I've run out of space here, so we continue on to the next page. Okay, so continuing the calculation, so this was the orthonormal base we were working with, and we've expanded g in terms of w1, w2, and w3. So to write g in terms of x squared, x, and so on, I need to plug in the vectors w1, w2, and w3, right? So this becomes 2/3 times w1, which is just the function 1, plus square root of 12 over 15 times w2, which is square root of 12 x minus 1/2, and then minus square root of 180 over 315 times x squared minus x plus 1/6. Oops, I forgot a square root of 180. So times square root of 180 x squared minus x plus 1/6. Okay, so now we multiply this out, right? So this is just 2/3. And then square root of 12 times square root of 12 is 12. But 12 over 15 x minus 1/2. This times this is just 180. X squared minus x plus 1/6. Okay, so to simplify things a little bit, let's reduce these fractions, right? So what is 12 over 15? So 3 goes into both, right? So that's 12 divided by 3 is 4. And then 15 divided by 3 is 5, so that's 4/5. And what is 180 over 315? So it reduces to 4/7. Okay, so now let's just multiply it out and collect the terms. Right, so in terms of the constant term of 2/3 plus 4/5, so minus 4/5 times 1/2 is so 2/5, so minus 2/5. And then minus 4/7 times 1/6. So 2 cancels out, so 3 times 7 is 21. So minus 2 over 21. So that's the constant term. What about the x term? So I have plus 4/5 x. And then minus becomes a plus, so plus 4/7 x. And then x squared, there's only this term, right? So minus 4/7 x squared. Okay, so now we just need to add these together, right? So 2/3 minus 2/5 minus 2 over 21. What is this in fraction? 6 over 35. So that's the constant, and then 4/5 plus 4/7 x. As a fraction, it's 48 over 35. And then minus 4/7 x squared. Okay, so that's what we get as our function g of x. Right, so this is g of x, and our original f of x was the square root of x on the interval from 0 to 1. Right, so we can compare the graphs of these two functions to see how close the approximation is. Right, so let's graph them. So first the square root of x, and then g of x is 6 over 35 plus 48 over 35x minus 4/7 x squared. Oops, x squared. That's not what I want. Let me start over. Okay, so 6 over 35 plus 48 over 35x minus 4 over 7x squared. Okay, and so we're working with the interval from 0 to 1. Right, so we're going to want to restrict to that interval. Right, so this is from minus 10 to 10. So we need to restrict to this interval here. Right, so let's change. So x goes from 0 to 1. And when x is 1, square root of 1 is 1, so y is also 1. So let's change y to go also from 0 to 1. Okay, so now if we compare the two graphs within the interval from 0 to 1, you can see that they're fairly close together, except maybe at the endpoints there's a little distance between the two graphs, but in the middle you can see that they're quite close to each other. So this is a fairly good approximation. Okay, so this was what the approximation looks like, right? So again, you have square root of x and also g of x.